And here we are at one of the cornerstones of chemistry, the periodic table. Um, it's a fairly iconic image, and most of you, I think, at this point are probably familiar with it. But its organization is not obvious. There are peaks at either end, there's a valley in the middle, there's the strip at the bottom that's not connected, and it's not obvious why we would want to organize the table like this. So we're going to break down some key terms, we're going to talk about some of the structure, and we're going to begin to really dive into this really mapping of the key pieces, that being elements that we use to build understanding in chemistry. So first and foremost, the periodic table is built on rows and columns. The rows we refer to as periods, as we will see those particular periods have specific meaning with respect to the structure. And the groups are called families, the columns are called groups or families. The families are things that have similar chemical properties. They tend to react in the same way, they tend to gain and lose electrons in the same way, and they're grouped into categories that have specific names that we'll take a look at here in a bit. And so we have this structure for the periodic table. Again, we ask the question why this strip at the bottom that's disconnected. And it's really only disconnected for the sake of presentation. If you'll notice down in the second to last row, we have element number 56, and then the strip at the bottom starts with element 57. And really, that little strip gets inserted in there into what's called the expanded periodic table. But the expanded periodic table doesn't fit well on a textbook page or a sheet of paper, and so this condensed form is typically used for that purpose. We can insert that strip in there, and we can see that the periodic table now is broken into what appears to be 4 sections. You have this first group of two, you have this first section of 2 groups or 2 families. We move on to this thin kind of strip here in the middle that we just inserted, which has 14 elements or 14 columns. We have 10 columns in the next kind of section and then 6 in the last. And of course, those are references to the Aufbau diagram and the different sublevels in an electron configuration. We have here on this first 2 columns are elements that are filling S sublevels. And the periods are what S sublevels being filled. So hydrogen is filling the 1S, lithium the 2S, sodium and magnesium the 3S, and so on and so forth. And as we jump to the other side, those 6 elements represent the 6 electrons that can fit into a P sublevel. Again, the first row, notice there is no group of elements in that P segment. Helium is slightly misplaced, but misplaced for a reason, and that's because that first energy level without the P is filled, and if we go then to neon, the second energy level, the 1S or the 2S and the 2P are filled. So helium is on the right side because its energy level is filled, not because its electrons are going into the P sublevels. We drop down into this next group and we see D sublevels being filled. Again, notice that the D sublevel doesn't happen until the 4th period, and when you are filling your first D sublevel, it is the 3D, which comes after the 4S. So potassium and calcium are 4S1 and 4S2, and then when you jump over to scandium, then you have that 1 electron, that 3D1. The little strip at the bottom is your F block, and so those are the electrons that are filling in the F sublevels. Again, the numbers, the period numbers represent the S and the P orbitals that are being filled in those particular arrangements, and we can see from this diagram that we've seen before that's the order of filling. You fill the 1S and then the 2S and then the 2P. When we go down to the 3rd period, the 3S and the 3P. But then as we follow those diagonal lines, again, remember the 4S fills before the 3D. And so our D orbitals are actually filling 1 energy level lower than the S that comes before. So those that D block is the 3, 4, 5, and 6D. And then again, if we follow the diagonal lines across, once we get to the 6th period, that's where our first F block exists. And notice as we follow those diagonal lines, directly after the 6S is the 4F. And so the F sublevels are offset from the periods by 2. And so we have the 4F and the 5S. And so we talked in class about using this diagram to build shorthand electron configurations using noble gas notation. And so for instance, what we'll do if we are trying to find an electron configuration for, well, let's take vanadium here, number 23. We're actually going to start by going back to the closest noble gas before vanadium, which is argon, and we'll put argon in brackets. And that accounts for 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Well, sorry, the argon stops at 3p6. And then after that argon in brackets, we're just going to continue on until we get to vanadium and write 4s2, because we have to cross that 4s block, and then 3d1, 2, 3d3. So the electron configuration for a vanadium atom would be argon in brackets, 4s2, 3d3. Talking about these shorthand configurations, here are some elements that you could take a look at. You should grab a sheet of paper, you should grab your periodic table, and see if you can write noble gas electron configurations for these elements. You should pause the video and write those down, and then the next slide will be the answer key for those, but you really need to make sure that you can do these on your own. So go ahead and pause the video and see if you can get noble gas shorthand configurations for those elements. And here is your answer key. Again, you can go ahead and pause the video and check the answers.